Good day. We, the Engineering Home Services, will be presenting our proposed four-story commercial building. The Engineering Home Services has been resilient throughout the years due to its employees' striving dedication, which leads to excellent work. Analyzing and creating a multi-story structure is both an art and science, and is something that is usually quite hard to do. It is hard because one has to look at broad range of variables and try and guess what effect each variable will have on the project. So, we will be having our journey towards the presentation of the proposed building. Our multi-story commercial building will be located at Tagum City along the National Highway here, the yellow part of the presentation, just beside the University of Mindanao Tagum City College uh, Visayan campus. As we look through our location, it is not that far from downtown, but it is the perfect location for the building as it is on the side of a multi-lane highway. So let me show you the perspective of our building. As you see in the picture, our building is majorly colored yellow and blue, in which inspired by the IKEA mall that is known all throughout the world. Our building consists mainly on W-shaped steel members, which commonly known as an I-shaped member, as it is best used for buildings because steel members are factory crafted materials, so it is already rated to a specific strength before distributing to the consumers. As for our walls, as you can see here, our walls are concrete with a heat strengthened glass which is semi-tinted to avoid much heat from the sun coming inside the building itself. The building also consists of an open parking space here in the side, beside the building covering the massive lot area of 20,000 square meters. Uh, so this will be the site development plan, which covers the floor area of 12,800 square meters and lot area of 20,000 square meters. So this is our ground floor plan. As you can see here, there are a lot of rentable spaces here in the side, in the middle, and in the middle. We have two elevators on here on the lower left side, beside the stairs, and we have the grocery store, the storage, and another elevator here, and the electrical and mechanical rooms, beside the toilet and the fire exit here and here, and oh, that's all. And we have two entrances in the back, which can also be used as exit, two in the side and one in the main entrance at the front. So in the second floor plan, it's pretty much the same. We have rentable space here at the side, rentable space in the middle, but we have an open space here that you can see the lobby in the ground floor. We have the electrical and mechanical room and the customer service here beside the toilets, and there are two elevators, and we have the department store here, and we have stairs also here. At the third floor, it's pretty much the same on the second floor, but the differences here is the things that is placed here on this section, which is the appliances here and utensils or home decor. It's pretty much the same on the other parts. As for the fourth floor, it's different from second and third floor because it doesn't have an opening in the middle, and we have way lot more of rentable spaces here than the second and the third floor. And the next one will be the roof deck. And we have here a little shed where you can go in and out of the roof deck, which can also be used as a chilling place, because as you can see here in our perspective, we have a high railings to avoid accidents happen when hanging out on the roof deck. So in the front side, in the front elevation, you can see it's pretty much made with it's pretty much covered with glass. We have here the big glass pane and the smaller ones. And on the side, we have here the fire exit, the two main entrances, and the fire exit at the back, and the mechanical room and electrical room here. These rooms, which this part of the plan. And as for the rear side, we have here the two entrances or exits. We have the fire exits here, and on the right side. It's pretty much also covered in glass with the bigger panes and the smaller panes. In the left side elevation, mostly covered in small glass panes with two fire exits. In the longitudinal section AA, which you can see here in the floor plan, the AA and the B. In the A, you can see the rentable spaces here, and you can see the cashier here, which you can see here, and the rentable spaces. As for the cross section B, you can see the rentable spaces in this side. So here's the schedule of doors and windows. As you can see, open back windows, color black glass, location outside walls, and open back windows in rentable spaces and offices. We have here the automatic glass sliding door for the main entrance and exits. We have the glass door for rentable spaces, and we have the steel fire exit door for the fire exit. And we have the wood door for the toilets. And now let's go for the structural plans. So here's the foundation plans. As you can see here, this is a massive building, so it is spaced in 10 meters. We have the F1C1. We have the same footing and column all throughout the first floor, spaced in 10 by 10. So here's the tie beam one, which is covered everything also. Uh, this is a 150 from here to here, and 110 from the bottom part to the top part. So here's the second and third floor framing. As you can see, here is the slab and the girder one. So it's basically the same all throughout, because we have the same size. We use the same size for a full floor, which also spaced at 10 meters. So our beams have 10 meter span all throughout. So it's basically 10 by 10. And as for the fourth floor plan, framing plan, so we basically have the same. Uh, it's vacant here for the elevators, and here elevators for, and here's for the stairs, and here's for the stairs also. So we don't have slabs there. As for the roof deck, it's basically the same. So we have the 10 by 10 with the slabs. The next one is the slab schedule. So we use the typical slab, which has a bar diameter of 10 mm, which is a two-way slab, which has 225 spacing at on center, which has a thickness of 150 mm. So it's a typical slab section. So as for the stair details, we use also a typical stair. So it has bottom bars of 12 mm 12 mm diameter, spaced at 150 mm as for the landing here, and as for the stair footing, you can see here the specification of a typical stair. As for the typical footing tie beam, we also use a typical for a footing tie beam, which has the here you can see 10 mm ties spaced at. So it's that the footing tie beam is a concrete, which also here you can see the a little column here. It is connected to the pedestal on the surface. So it's also reinforced. As for the schedule of beam and column, we have a we have two types of W-shaped beam. The W-shaped member section. The first one is a W40 by 593. You, it has a depth of 1.09 meter. It has a zero point 0.4 for the flange, and it has a 0.08 thickness and a 0.05 for the width of the web. As for the girders, we use a 36 by 361 steel beam section, which has a depth of 0.97. It has the flange width of 0.42 meters and a web thickness of 0.03 and a flange thickness of 0.05. So here's a typical bolt connection for the steel girders. Mm, and here are the notes for structural steel works, and this will be the construction notes. So that would be all for the architectural and structural part of the presentation. So here is my co-worker Romarc Vergara for presentation of our STAAD analysis.
So good evening, sir. This is Romarc G. I am presenting about the our structural analysis. So this is our structural analysis model of our multi-story structure. It has a height of 21.2 meters and a total weight of 229,637.175 kilonewtons. Um, this is structure. It is it is supported by fixed support, and and it has a release. It is a release of moment so that the member uh, will work optimally, and it means preferable to keep the I beam using plane moment and use release to avoid out of plane bending and torsion, and so that some releasing some degrees of freedom make the structure more efficient and enhance design ratio if locations of release is estimated correctly. So for the our properties, we use the plate of 200 mm for our stairs, and for our columns, for our beams, we use the double shape 36 by 361 steel, and for our columns, we use the W shape 40 by 593 steel. For the materials used, it is purely steel, and this is for the specifications. We input for diaphragm for the first here, second, third, and for the fourth. And as I said earlier, it has the recess for MOX, MY, and MZ. So for our loading, for the definitions for reference load, we calculated our dead load by using this in ECB. The dead load for at the section 204. For the dead load of residential spaces, we calculate it by floor, and for the hallways, it is slightly different because hallway and residential spaces are different in loading. And we calculate our loads from second floor, third floor, then third floor to fourth floor, and fourth floor to fifth floor. The loading used in this structure, it is really based on NCP 2015. We base the dead load, dive load, seismic load, and the fluid load in this NCB. And for our our deck rough deck floor loads, we use a 23.6 for the concrete, and we use a 400 millimeter slab. We also calculated the loads in our inner walls and for outer walls. For reference load, you need to create the self weight, and this is the loads that we get from these calculations. This is the dead loads for our leg loads here, the 1.9 GY and the 4.8 GY. For the residential, we use the 1.9 kilopascal per load, and for the hallways, we use the 4.8 kilopascal per loads. And for our roof live load, because we don't have a roof and our slope is 0.0% a flat roof, so it is 1 kilopascal. And for our our fluid load, the 21.582 GY, we calculate it by using the 9.81 kilojoules per cubic meter, and we multiply it by the height of the tank that we use, which is 2.2 meter. For the seismic load, we get these parameters from from NECP. For the importance factor 1, which we could see in table 208-1, we use 1, and for the seismic zone factor, we use 0.4, and because it is a special reinforcement concrete frames, the R we use is 8, and for the soil profile type, it is type D, and for the seismic source type A, we also get the nurse's factor, which is 1, and for the nurse's factor of NV is we interpolate it and we got 1.156. And for the seismic coefficient CA, we get 0.44 times 1. And for the CV, we get 0.64 times 1.156. So we'll go to the load combinations. As for the load combinations, we taken it from section 23 of combination of loads by using the load combinations using strength design or load resistance factor design. We also use basic load combinations using allowable stress design and special seismic combinations, which we get here. So these are the basis of our combination load combinations for the basic load combination using the strength design or load and resistance factor design. So the basic load combinations. And also for the load combinations using allowable stress design and alternate uh, no, no, no. alternate load alternate basic load combinations and the for the earthquake the special seismic load combinations which you can see here all the loads we use. So the earthquake base shear uh, is checked by using Excel and manual calculations. It is done by using seismic design of building structure, which is here. So we base it from this lateral force or the static lateral force procedure. So in this we should get the V, which is the base shear, the C, the V, or the still the base shear and the CA, and the minimum base shear and also the maximum base shear. So this is our parameters. This is the parameters that we use. And for our total weight of structure, we use calculate by using this Excel, where we select our what sections of columns and girder we use, and we will input the quantity of the columns and the length of the girder, and also for the wall and its weight. Then by using the tributary area, uh, we get the area for the hallway, which is two-way, and for also the room area of rooms, which is two-way. So by using this Excel, we can get the total weight of every frame in this structure. For this frame, and so this frame, and so on. So by using this Excel, mm, we calculated all the total of all the weight of every frame from second floor to the last floor. So after that, we calculate the total weight of the structure, which is we get this 229,637.175, and to design the base shear, we use this. This is the manual calculations that we made for the base total design base shear, and for the minimum base shear, which is this is what we get, the 225,181.99. And for the minimum base shear, which is 10,618, and for the maximum base shear is the 315.7. And 31,375.11. So that is the manual calculation, and this is the calculation for base year using our Excel program. We just input here the CV, the I, the CA, the Z, the NV, the R, the weight of the structure, and of course the T. Then the program will automatically calculate it. It will calculate the maximum base year to be used. In this structure, it is 331,475 because it is the max. It is just the same here. So now back to our stud. So after we created the structure, we input properties, and then the materials, and then the specifications, and the supports, of course, and also after computing all the loadings needed here, transfer it to here, the reference load definitions, and the seismic load definitions. And after that, after we input the load combinations, and then we can run now the analysis, the structure. So after running the analysis, we got zero errors and zero warnings for this structure. So that's all for the structure analysis. Thank you.
So next in line will be Jason Dupra for explaining our design computations.
Hello everyone. And now let's go to the process of designing beam and column. First, the beam. So as you can see, as you can see, the Excel is already finished and ready to solve and give the proper and exact value that we need to designing beam section. So in first setup, we need to find the exact value of section given by its properties and the beam properties. So and then it gives its own properties by selecting one kind of section. So you can choose different kind of section. And then using knowledge and formulas and understanding the topic of this subject, we gain the proper of solving the exact section of the beam. And then it will give computation for checking in compact, for flange, and for web. You can locate it in table 502.4.1, limiting with thickness ratio of compression element. And then it will give you the proper saying if it is compact or non-compact. So, or slender ratio. And then step two, so you can determine the LB, LP, and LR. So using the formula of NECP 2010 or 2015, it will give the LB, LP, and LR a proper answer. And then zone 2. Zone 2, the inelastic region, solving lateral torsional buckling, modification factor, or the CB. So the MA, MB, and MC, or the left, center, right of the section. And then MMAX. So with the formula of CB, you can solve CB. And then calculate MN in plastic region, in elastic region, and elastic region. So, and it will undergo the process of, ganun siya, yung step zone 1, zone 2, and zone 3. And then, and near to the conclusion. And in this side of this Excel, this is our result in stat output. So in this kind of critical section. And then we can compare and analyze if it is the solved problem or the solved section is nearly acceptable or not sa STAAD. So and then for the column, same as the beam, it need data, beam properties to solve and understand in solving the column section, and then it will go the process of data analysis. So as you can see, there will be finding LB, LC, and LU using the formula, and it will give you the next step. So it will proceed to with crippling or proceed to with slender. And then, so with crippling, it will for checking for compactness. Yeah, checking for compactness, and then after gaining the compactness results, you can solve the flexural bending stress, the FB1, FB2. Actually, si FB1 and FB2 is from NSCP code 2001. So we will not going to use it because we never stated nga 2001. So ang ginamit natin is 2010. So and then we will using FBX, FBY, the FBX and FBY. So the added all together. So it should be less than 1 to make it safe. And then checking for actual, M actual, so it will be safe again. The value of K will determine if it's both fixed, one hinge and one fixed, both hinge, or one free and one fixed. So it will be determined by that different kind of values. So, and then using the value of K, you can solve the KL over R in x-axis, KL over R in y-axis, and then using the maximum of those two, you can get the KL over R, and then solving for CC. So next is identifying if it is short column or long column. So and then KL over R is less than or equal CC, that should be short column. Then long column, KL over R greater than CC. So si KL over R is less than CC. So nabutang siya sa short column. So it will solve FE, the lambda, FS, and the F, then si P. Then using LRF, the PU is equals to, ganun siya, solve nun siya. And then the demand capacity ratio. So ganun siya, C over D is greater than 1, so it is safe. And the result of our STAAD, critical section. And that's all. This is Home Engineering Services. Thank you.
So, in determining the critical section, we check the STAD output for all the ratios, and we look for the ratio that the highest ratio in every floors and every columns, and we use it for the reference in designing in the Excel for choosing that beam, that specific beam number for our design. So that would be all. Thank you and Merry Christmas.